So he's going to speak on weighted ROC and Murphy curves in cost space and applications.
Okay, thank you, Joanna. This work is motivated just by you. We had some exchange of ideas about the generalized probability integral transform, reading your paper on probability forecast, tail forecast. And after that I got the papers from Timo. I understood many things. I'm very new for this community. And I tried to modify a little bit the typical thinking in probability forecast, and somehow these are the prior works that I use. Somehow the works of Timo indicated me the papers of this Spanish guy, Oralu, which proposed ROC analysis in co-space. He got some good results, but he postulated thresholds, but he didn't derive these thresholds. Okay, he got some, he introduced some cost function, cost, but this cost was assumed uniformly distributed, which is somehow far away from the reality. And after that I found a paper by some Chinese guys who suggested to use not the uniform distribution of the cost, but somehow after we tried to get the corresponding costs, we discovered that there is some error. We did a contact with Chinese guys, but they didn't respond us, so we began to fight with the problem. What happens is we used the so-called Lame-Cooler curve, which is probably unknown for many of you, because why I'm beginning with this Lame-Cooler curve, because it's a key point in our results. And here are given, somehow this Lame-Cooler curve is some non-decretion function, and it is used in informatics, in economics, to quantify the wealth, how the money are distributed between the rich and poor people. And it is related with so-called Lorentz curve, which is more popular probably. And somehow this Lame-Cooler curve, I denoted by K, is given by this expression. It is 1 over the mean of the random variable, and integral goes from 1 minus p to p over the inverse function. What is funny, here you can see the Lorentz curve has the same behavior as a ROC curve. It begins from 0, ends at 1, it is non-decreasing. So it is a distribution function of some random variable. Okay, the ROC also. But also it's what called me attention and gave me an idea to use this Lame-Cooler curve, is that Gini coefficient is 2 times area under the Lame-Cooler curve minus 1, which is the same relation with which has the ROC, the AUC, in fact. Also the Lane-Cooler curve is in fact, the distribution function so-called Bradford distribution. And this Bradford distribution is just shifted Pareto distribution. So this Bradford distribution is very useful to model the extreme events. Anyway, this is some very preliminary information just to justify why I will use the Lane-Cooler curve in the next steps in my representation. So I'm turning to the binary classical classification setup. I consider the pair of random variable z and y, where y is this Bernoulli random variable with outcome 0, 1, and z is chance of occurrence of this event. So z is calibrated if this conditional probability y equal to 1 given z equal to z is equal to z. So the goal always is to predict this conditional probability y equal to 1 given the information, given our observations. So in this moment I'm defining this cost-weighted misclassification loss. I put some penalty for loss false positive cases. Okay, this penalty is some c between 0 and 1. I'll consider this as a random variable in one moment. And another penalty 1 minus c when we have a true negative case. Okay, and one more c 1 minus c when it happens that z and tau is our threshold. And in continuous case, of course, this last term will disappear. So I'll consider this my penalty function in the following. So what is interesting here, our threshold decision theoretic approach. We have to minimize the expected loss. We consider this C random variable in 0, 1, not necessarily uniform. And somehow we will try to find the optimal decision functional of cost. And if we find it, we will denote it by y tau hat. So the expected loss surface, this is the mean of probability, joint probability on the random vector zy, and it will reveal performance variation driven by this constitutive threshold. So we'll consider this expected loss over the full cost range, and you will see that we can summarize by, this can be summarized by Murphy curve. And Lane-Cooler curve will be used to determine the Lane-Cooler ROC version. But let me show the first interesting result. So if we have our random variable zi defined in the probability space, and our z is calibrated, we consider this classification decision rule y hat. Okay, just to remind, this cos c is the penalty when we have false positive case, 1 minus C when we have false negative. Then the optimal threshold tau star that minimize the expected cost modification, cost-weighted misclassification risk is just tau star equal to RC. And the optimal, the associated base optimal decision rule is given by this relation. Okay, here's a sketch of the proof. And now Murphy curves. What happens if Z is our random variable in 0, 1, and S tau is our cost function, or more this S tau was defined here, okay? Then we define the Murphy curve as a map depending on this tau, which is 2 times this expectation, where again the measure P is the probability, joint probability distribution of this Z and Y. So the result is the following: if this S tau, our functional, implements the base optimal rule on 0, 1 asymmetric loss with cost C, there is a 1-to-1 correspondence between threshold and the cost. So if we have our Murphy surface, the optimal decision is just here. And to give another round vision of this result, this is the surface maps the expected loss over tau and C, shaping the decision landscape, this red line just. And what I do after that, we define the Murphy mass. And the Murphy mass is just this green area under the optimal decision. Also, it's defined by this integral. And here is the theorem. Somehow, as you might expect, if the cost is uniform 0, 1, we just recover the mean Braille score. Okay? And now, here are the usual definitions of ROC curve, but now we consider the threshold as a function of this C. And so our generalized AUC functional, which is below this ROC curve, is given by this expression, where Fc is the distribution of our cost. And this is an interesting lemma which describes the base optimal thresholding, which connects ROC and Murphy curves. And the statement is the following: if Z is calibrated score and FZ1, FZ2 are the corresponding conditional distribution functions, somehow, FZ1 and FZ2 are FZ0 are given here, okay? So, under this cost-weighted 0, 1 loss, when this threshold depending on C, which is our result optimizing, the generalized AUC reduced the classical form under base optimal thresholding. So there is one-to-one mapping between the ROC, depending on C, and the expected loss. And here I already I involve the Lane-Cooler curve. And if you remember, it was defined by 1 over the mu integral 1 minus p to 1 of inverse. But now I'm considering just the distribution function of this Lane-Cooler curve. So we have another Lane-Cooler, the so-called Lane-Cooler ROC curve. Okay, and okay, here are some results related with this Lane-Cooler ROC curves. There is some one-to-one correspondence between ROC dependent and tau and Lane-Cooler curve over this ROC. And our conclusion is that the Lane-Cooler curve is invertible and fully encodes the ROC behavior under the cos. Okay, I have some other examples, but just to finalize, in the left side are written the classical ROC curve's properties. It plots true positive versus false negative as a threshold varies. Lane-Cooler curve aggregates ROC values over the cos contours. Okay, some other improvements, in my point of view, of the classical ROC curve in the left side and Lane-Cooler ROC curve. Okay, what happens? The Gini coefficient is again 2 times this our extended ROC Lane-Cooler ROC behavior. I'll stop here. Okay.
Thank you.
Thank you.
One question specific to Nikolai, otherwise I will continue with the discussion. Yes, Timo.
I have one. So, what I didn't get in this Hernandez or Paulo paper when I was reading it, they have the tau and the C to be unequal, or possibly unequal. But in the Murphy curve, the tau and C must be equal, and then you get all strictly proper scoring functions. So what's the motivation of having tau and C unequal?
Tau and C unequal. I'm following this optimal base decision rule.
Okay.
Let's thank Nikolai again.